Hi everyone. My name is García-Lahuerta, and I'm going to present my thesis, which, as you see, is about modeling of advanced electrodeless plasma thrusters. I'm doing it under the supervision of Mario Merino and Eduardo Aido in the framework of the Zarathustra project, which Celian was talking about. First, basically the contents of the presentation. I'm going to give a brief motivation, very fast, because Celian talked already about the magnetic arc thruster. Then I'll state the main thesis objectives, and I will also talk about the model and how we integrate it. And in the end, most of the time I will spend explaining the results of the last simulations that we've been running and that, as Celian said, will be presented in IEPC next week. And then I'll finish with the next steps for the following year. As Celian said, the magnetic arc thruster is a novel design for an EPT that was patented here in the EPT group. And as he said, it has, in principle, some advantages with respect to traditional EPTs, as reduced wall losses and smaller plume divergence. But it also presents some challenges in terms of the simulation. First, now we have a fully three-dimensional problem, which is computationally expensive. And we also have complex geometry. We have two ion streams coming out of each nozzle. And therefore, we are going to have a collision between them. So we can have structures such as shock waves and many others that might appear in the symmetry plane. The main objectives of the thesis is first to understand the major physics of the magnetic arc thruster, and now I'm paying special attention to the external part of the thruster. We want to see how the plasma expands into vacuum in the magnetic field, and we want to study the effect of the self-induced plasma magnetic field, which we expect to be quite important in the expansion. And then we are also going to study the plasma detachment. And to do so, we expect to have, by the end of the thesis, complete fluid code for the simulation of EPTs that could also work not only for the magnetic arc thruster, but also for standard cylindrical EPTs. We're using right now a very simple model, which is a two-fluid model with, we're considering a quasi-neutral collisionless plasma. With massless and polytropic and perfectly magnetized electrons. Under these conditions, we find that the electron equations are simply algebraic. And we are using cold and singly charged ions. We are solving for the time evolution of the problem, although we are mainly interested in the stationary solution. And right now, I will discuss it later, but right now we are using the beta zero limit. We are not including the self-induced magnetic field of the plasma. These are the standard fluid equations for plasma, for a two-fluid plasma. In blue, you see the momentum equation of the electrons, which in the end reads something like that, which is, as I said, just an algebraic equation for the conservation of electron energy. These here are the equations that in the end are going to be solved, and you may see that they recall pretty much of the Euler equations of compressible gas dynamics, but with the exception that we have a forcement here that is the one that's driving, that's the plasma. How do we integrate the model? We are using a discontinuous Galerkin method that offers many advantages over traditional finite element methods and also over finite volumes. First, the method is local, even in high order methods. It's also conservative, and it allows us to have what we call HP adaptivity. We can refine both by refining the mesh and also by using higher order elements in the discretization. And also, one advantage is that it allows us to have a semi-discrete form, so we can discretize in time in with whatever scheme we see we see fit. Usually we're using a Runge-Kutta time-stepping algorithm. So I'll go on now with the simulations and the results. What's the setup that we have? Right now we're solving a 2D problem to start with in planar geometry. So we are considering the z-axis, the x-axis, and the y-axis where we wouldn't have any gradients. We have a symmetry plane here, as we just simulate half of the domain, and we input density profile there in the red line. I hope you can see it. We input Gaussian density profile with a radius of 1 and supersonic inlet velocity. The other boundaries are just supersonic outflows. And what's the magnetic configuration? We're using infinite wires, which is the planar counterpart to a standard coil, with twice the radius of that of the plasma density. This, as we said before, fixes completely the map of HE, which is quite important because in the end, it's the main force that's going to is what's going to give us the magnetic force over the electrons. That's going to be the main driving force of the plasma. What are the results? The results then, as we see, the initial part of the expansion is very similar to that of a standard magnetic nozzle. We have the magnetic field confining the ions radially and accelerating them axially, well, in the z direction. But as we advance and the ions find the symmetry wall, we have an oblique shock that appears here. As we see, all density, temperature, also electric potential fall axially until they find the shock where they rise with the subsequent reduction of the ion velocity. However, this reduction, and this is important, is not big enough to stop the ions from moving downstream. This is quite important because if we stop the ions completely, we wouldn't have any thrust. Here I show you. Here we can see a little bit better some of these features. As you see here, this is the X component of the magnetic force, and as we see, we have a radial confinement in the first part and an acceleration in the first part. However, in this part here, I think here it's very it's not too clear, but we have a negative force. So we have a drag on the ions in the part where the shock appears. We can see that very clearly in the integrated magnetic force, which clearly rises until around 7, 8, which is where the shock appears, and we have this drag that reduces the thrust. As we said, we are not including right now the self-induced magnetic field of the plasma, but we are expecting this self-induced magnetic field to be quite important in the expansion. So to gauge that importance, we calculated the self-induced magnetic field for these simulations here. And as we see, we find that the behavior is what we expected. Here we have the beta zero limit, which is the one we solved for. And as we increase the beta, this is the importance of the self-induced magnetic field, we have that the self-induced magnetic field is pushing the lines outwards. And as you see, this geometry is quite different to this one and much more different than this one, because here we have closed magnetic streamlines, and that doesn't allow the electrons to flow out of the domain. However, here we have the appearance here, you can see it very clearly. We have the appearance of a separatrix point. This is a point where the magnetic field is 0, and this opens completely the magnetic line. So that way we can have an electron current going downstream that will be able to neutralize the plasma and therefore avoid, in principle, this effect. That's all for the simulations, which, as Elian said before, will be presented in the International Electric Propulsion Conference next week. The next steps for the next year in the thesis, in principle, is to add the self-induced magnetic field in a self-consistent way. So we have to feed this magnetic field topology back to the simulation and repeat that in an iterative way until we reach convergence. We also want to make a parametric study on how much the parameters of the simulation influence the results. For example, the magnetic topology, the radius of the infinite wires, or the map of HE, etc. One of the main goals is to make the 3D extension of the code, because, as I said before, we can have effects in 3D. The problem is fully three-dimensional, so this 2D simplification is not really satisfactory. And we, as well, could extend the model, because we're using now a quite simple model, with the addition of neutrals, collision, electron inertia, and many others. So I think this was it, and if you have any questions, I'll gladly answer.
All right.